substitution method. And we've been using U substitution for one variable a lot, right? But there's a different substitution method, and I'm saying this is not the U substitution method, right? Because if we usually write U equals the stuff in terms of X, right? Like this, and then you differentiate it and multiply the reciprocal. But it's opposite. X in there is replaced by something else out of nowhere, not the expression you see in that integrand function. Somewhere, something different. Then this dx dt, you calculate h prime t, is appearing directly there, not the reciprocal. It's a different type of substitution. So for example, if you see 0 to 1 over 1 plus x squared dx. If you're asked to integrate a function like this, right, then you think about U substitution, right? You try many times and realize it doesn't work. And then you pull out this type of substitution, correct? Different kind. So what is a substitution here? What is x? Anybody remember this? Right. Out of nowhere. Yeah. It's a tangent t. You pull this one out, tangent t. Don't ask why. Just see what happened with this one. Okay, they said this is going to work. And then let's see if that works. And the dx dt, right? What's dx dt? Secant square t. Now when do you reach x equals 0? When t equals 0, right? When do you reach x equals 1? Pi over 4. That's the standard range there. So that integral changes to t equals 0 to t equals what? Pi over 4. When do you reach that x equals 1? When t is pi over 4. Then you substitute it. What is 1 plus tangent squared immediately? That's the motivation, because we know something about 1 plus tangent squared. Who remembers about 1 plus tangent squared? Secant squared, right? So that becomes a secant to the 4th power. Then you multiply derivative, not the reciprocal, just derivative itself, right? dt. They're claiming this definite integral is equal to that definite integral. That's what we're saying, right? So how do they cancel? Yeah, secant squared, but if you flip it, it's a cosine squared, right? Who remembers how to integrate cosine squared? Right, the reduction formula from pi over 4, 1/2 plus 1/2, what is it, cosine of 2t, right? Now you see that one is easy to integrate, that one is also easy to do more square, 2t is a constant multiple, right? We're happy here, right? It works out. But just you got to know what to do. You have to pull this one out on your own to make this happen, right? Okay, so let me interpret this one in slightly different. This is what I've been doing technique-wise. This is how it's happened. Here's the function x equals 0 to x equals 1, right? If you sketch the graph of this one, is a bell-shaped graph, like this, dramatically going down like that. Okay? In one-dimensional case, there is not much geometry going on, so it's not much of a motivation. But what we are doing here, this is our space x. This is our domain. And they reparameterize this one with a t equals 0 to t equals pi over 4. This is x reparameterized by tangent t. So if I divide this one equally like that, then this one will divide equally like that, right? No. Tangent t does not take this equally distributed t value into equally distributed x value. It will be unequally distributed x value like that. So if I have tk minus 1 and tk, they're corresponding to xk minus 1, xk there, right? But they're not regular. They're sometimes larger and sometimes smaller, because tangent t is not a linear function. It's taking everything into different range. So it changes all that. So in two-dimensional case, which is double integral, this domain it's not this simple like line. Sometimes it's a square, sometimes it's triangle, and sometimes of this projected image of a cylinder cut out like that, funny, like in the test, right? So we reparameterize like this one and reformulate it like this. There's original integral, and change x and y because that's our domain, right? Two variable function with a two variable like s and t, and figure out, what the map is to reparameterize the whole thing. Then there is this thing coming in, and I gave you the name for this one is the Jacobian factor, right? So that's how it happens. If you parameterize, these are final words. If I happen to have this parallelogram here in xy plane, using the vector method, you can nicely reparameterize it with a s and t, so that s and t varies freely from 0 and 1 here. S and t varies from 0 and 1 freely, not depending on each other. Freely, that'll cover this vector and that point as you dilate these two side vectors. So the integral over d of f of xy dx dy, you can see if it's parallelogram, both direction projection, do you see that you have to divide it up like 4 different regions? This formula there, in between that formula is ugly if you do it this way, right? But if you reparameterize like this, you enter this one. I'm going to call this region capital R. Capital R, this is good. 0 to 1, 0 to 1, right? So here's a capital R. And then if you figure out what this x is in terms of h, s and t, what this y is in terms of s and t, then you plug in those parameterization in here, and you can change it to ds dt. Okay? Then integral of this one is 0 to 1, 0 to 1. Beautiful, right? But you got to multiply what factor? Jacobian factor. I introduce the notation. X and y is now parameterized further like this, right? And then there's a matrix that we calculated before, 2 by 2. Is determinant. Turns out to be the right factor. It's a stretch factor. If I take a little bit of a square here, how does this one correspond in there? It's stretched out a little bit like that, right? It's not the same area. Its multiplicative factor is there. That's this factor. So this is the analogous version of what you did in the trigonometric substitution before. This one in here, and x out of nowhere, you pull out this tangent t by analyzing the shape. We're going to pull out this parameterization. Then you can write down this ugly integral to beautiful rectangle integral with this one formula right out there. And this is really cool. Think about the ideal. It's really cool. And the vector v, w, remember vectors, right? And then it's a vertex 0, 0, and parallelogram. Were you all able to picture the parallelogram? As far as I know, that parallelogram is not a rectangle. The angles are not 90 degrees. And then if you sketch that and try to compute this integral, and hope you able to pull out those boundary that I put it in there. So this is x-axis and this is y-axis. This is 2, 1, just roughly there. That's v, this vector there, right? And negative 2, 3, that will be somewhere about here. That's another vector. So that's the parallelogram I'm talking about. And when you're calculating this, you might feel like, oh, we're lucky that because they lined up nicely like this, so they only have to divide into 2 regions, right? But something happened to your brain that you decided to do, like this way over the y, and then you can see, oh, this and that. If you fix y and integrate over x, then you have to go from here to there. They use this formula in this region of y value. You have to use this, then this formula. In this region of y value, you have to use this and that formula. You have to divide integral into 3 pieces, right? But in general, that's how what's gonna happen. If it's lucky, these 2 vertices lined up vertically perfectly. But if I tilt it a little bit, then you can see both way you have to deal with the 3 different integrals, right? and you calculate this line and that line, equation of that line to break this integral up. And then I wrote the answer in this form. So I hope this answer made sense out of this by looking at this one and here. So did that make sense? Yeah, you're looking at this region 0 to 2. Oh, that line is negative 3 over 2x. That equation is 1/2 x plus 4. So we're integrating in between this thing. Between negative 2 and 0 for x thing, then you're integrating from here to there. That's different equation of a line you have to calculate, and so on. So this answer makes sense, roughly? You have to calculate the equation of all these three sides and look at this negative 2 to 0 for x value here and 0 to 2 for x value there, and integrate vertically first. Any question? So P and Q, that's actually what I did. And I was saying before, this integrating over y like that is better than the other way around because there's only two regions. The other way around, you have the three integral you have to deal with. Any question about part 1? Is that right? Yes. Yeah. Probably if it's 16, it's not a coincidence, right? So there's probably some explanation to it. But this would be reasonable approach in terms of what we've been doing before, right? Yeah. Any other comments, questions? Right. Then were you able to make a connection to the second part there? His question? This was a different way of doing it. So we're looking at the same region and same integral problem and introducing a different method. Let's see that the vector v and w, that's still 2, 1, and that. And I was asking you to explain that each position inside this parallelogram in here, for example, any position there, let me redraw it here. Not necessarily 90 degrees. This is vector v, this is vector w. Arbitrary position in here. How can you explain this one in this form? S times v, t times w, right? The idea is that you draw a parallel line that is parallel to w, another parallel line here that is parallel to vector v. Okay? Then because this is a parallel to that, that is parallel to that, this dotted line with that one makes a parallelogram, right? So if I use this vector and that vector, if I add these two vectors, you're sure we're going to end up at this diagonal vector, right? Parallelogram law. So what kind of vector is this one? It's a contraction of vector v, right? So that must be scalar multiple times vector v. And sure, s is less than 1 because it's inside, right? How about this one? T times w? That's also a contracted version, so it must be scalar multiple of w, which is smaller than 1, the scalar. So any position you have it in there, it'll be described in this form, SV plus TW. Or if you have an SV plus TW, where S and T are in this range, you're sure you ended up in somewhere inside this region, right? Without any overlap. It's like a new coordinate system, right? Okay, so if I put this 1, 2, 3 line in there, the 3 divisions, and 1, 2, 3 line, 3 divisions. If I look at this point, xy coordinate, it'll have some different coordinate, but in terms of this s and t, this is 1 copy and 2, this is 1/2, 1/3, and second 2/3, and s equals 1, right? S is chopped into that pieces. But it is not the same metric. The s equals 1/3 here. That doesn't mean this is length 1/3. It's all stretched. And this one would be w being 1/3, w being 2/3, and w being 1. So I would say this one would be 2/3, comma 2/3 in terms of s and t. So like putting a new coordinate system, right? All right. So hope that explains the first part there. Make sense? Everything is kind of reparameterized in terms of v and w. How about this one? If x and comma y is s times v, which is 2 comma 1, is that right? T, negative 2 comma 3, correct? Then you just expand this one. As you can see, 2 times s, x components, negative 2 times t. Y component s, y component here is 3 times t, right? So this is x comma y. So we manage that every position in here is described as 2s, x is 2s minus 2t, y is s plus 3t, while s and t varies from 0 to 1. Okay? So x is that, and y is s plus 3t. Okay? And s varies from 0 to 1. So ask you to compute this Jacobian, which is defined to be like this. Okay? And I'm going to explain the meaning of the Jacobian after we compute this one. So this is x and y, and in matrix algebra, x comma 5 comma 3 is converted into a column vector and multiplied to the matrix. So things are better in a column vector. So that's why you see x comma y there. That's how you remember the shape of the Jacobian. Enter column vectors. You remember that part. Then x comma y is here. Differentiated with respect to s, right? X comma y there, differentiated with respect to t. In that way, it's kind of consistent in there. So you write down x comma y there, right? You look at that, differentiated with respect to 2, right? With respect to s. What is this one s? That's 2, correct? This one in here? It's 1. Right? How about here? X comma y vertically with respect to t, negative 2 with respect to 3. This is the Jacobian matrix. Okay, so you calculate it. So what is the meaning of this one is the following. I call this one a parameter space, but let me give you slightly more physical meaning to it. Suppose we have an observer living in this world. What they see is this ST plane. The other guy observing the same world, but their coordinate system, they're here and they're there. They're the center of the world. And we're looking at same world in 2 different lenses. This and that guy they don't know, but their eyeballs are altered, surgery, so they don't really see the reality. Some distorted reality. So this guy sees that, oh, this is the parallelogram I see right there. But somewhat eyeballs is bent around. The guy in the ST plane, he sees it exactly as a perfect square. But it's the same thing that exists in our space. This guy sees like this guy sees like that. Because their eyeballs are manipulated. Make sense? So, the things that you see in there, for example, if this one did divide all world into 9 pieces like that, what he sees is that, oh, there's a square right there. Well, what this guy sees is that inside there's a parallelogram. The same thing is all bent around, right? These guys are not sure that if he's seeing the reality. But the relationship between these two things is described by this one. Okay? Alright, so the meaning of that, oh, I see this region, they're communicating. I see this region, I see that region is exactly delta s times delta t. Does this notation make sense? You chop that s, delta s into, delta sp, delta that. Well, this guy sees that, that's not the number I see there. Different number, right? So that factor is exactly this side correspond this vector and that vector. That tiny vector turns out to be xs, whatever this formula we have it in there, xs times xs ys. That's the vector they see. Here is a horizontal vector, right? And what this one sees that is this vector multiplied by delta s. Okay, this is scalar, and that's a vector. This vector turns out to be exactly that to him. So the other one, like that, turns out to be delta t of xt yt. Exactly, because it's a linear. If this function is not linear, it's a slightly non-linear bent around, this is approximately like this. And this approximation is good enough to capture the area of this region in 2D. Right? xy plane and st plane. Right? If the area to st guy is looking at this one, delta s times delta t, what is the area this xy guy observing? The answer is that the area of st multiplied by what? The determinant of these two matrices. That captures the area of the parallelogram. So that's determinant of xs and ys, xt and yt. You know the determinant is sensitive to the order of these vectors, right? So if you happen to st and parameterize it in the wrong way, then this might pick up a negative number. We call it opposite orientation. So when you parameterize this one, you have to be sure that you're parameterizing correctly so that it, left to right, counterclockwise is preserved. This horizontal vector and vertical vector, so this vector coming from horizontal, this vector coming from vertical, must be in counterclockwise rotation. In three-dimensional way, how do you measure the correct orientation? Right-hand rule, right? So if it is correct orientation, this will pick up positive number, not negative number, things like that. So if you know it's the correct orientation, you don't have to worry about putting absolute value or anything. Okay? So because of the world here is stretched around, you have to multiply the stretch factor called Jacobian factor. Then what is happening over that, fxy, you just simply multiply that thing in there. So hence the formula is formulated like this. All right? Here we are multiplying this tiny parallelogram multiplied by area of the multiplied by f of xy, right? That's the Riemann sum, correct? Does that make sense? But this one in that case is exactly equal, not approximately equal, exactly, because it's linear. It is that delta s times delta t times the determinant of the Jacobian times f of xy. Now, since everything is in terms of s and t here, right? You have to plug in st version there. Instead of adding up this one is not like chopped up in parallel like that. This region D is divided into slightly different fashion than usually horizontal chop up and vertical chop up, right? But it should still give you the same conversion number, and they're looking at it in this way. Once you enter like this, you know delta s and delta t came from this parameter space where things are nicely just 0 to 1 and 0 to 1, right? Yes, sir? Shifting, not only is it shifting, but stretching too. Yeah. If it is a shifting, it's not going to change the area, right? So rotation does not change the area. Reflection does not change the area, but if there's a stretching is involved, then it does change the area. So Jacobian is especially sensitive to stretch factor too. If it is a shifting, Jacobian factor will turn out 1. Therefore, you don't have to actually do anything. Hope that makes sense. Yeah. So that's the stretch factor, and then that's the Riemann sum. So if you look at it as just a formal Riemann sum, it's the same as there's a ds dt, and just simply integrate the whole thing, right? And that's what this formula is about. Instead of integrating xy plane, integrate over parameter space st plane over this new region R, and integrate the whole thing. What's the advantage of R? Simple, 0 to 1, 0 to 1. This is very easy, a lot easier in terms of iterated integral, right? And that's the main purpose. Reparameterize this world through the different lenses, and then your integral might be cleaner. That's the whole idea. This is not the usual motivation of one variable when you substitute, right? It was more about what's going on inside. But here, we're motivated about how this one looks like, then we're doing something different. So slightly different motivation if you want to make an analogy with one variable calculus case. When you change the various substitution, you multiply something there, right? That's exactly what this one is, Jacobian factor. But the motivation is different. All right? So in that case, I think the answer here is this one. So original thing, this is our original problem, right? Integrating that, but you look at it in the parameter space ST, like a different observer of the same phenomena, and R in there, that's the rectangle, 0 to 1, 0 to 1. And there's x plus y, but this should be written in terms of SNT as well. And what is this one here? Jacobian factor. There is no SNT here, right? Because it was the connection was linear. In general, it's not linear, and you will have SNT in there too. But because the linearity is all uniform stretch factor all across. So x plus y here, that's 8 go outside, and this one is replaced with x and y, the parameterization we had, and this whole thing changed to now iterated integral for s and t. We can see here, this is a lot easier. And answer turns out the same 16. That's the meaning of that exercise. Good? Question? All right. All right, what's this? What is this called? Not cylindrical, not spherical. What is this one called? Polar coordinates, right? All right. If the region is like this, and if you integrate it, y first, given x value here, how many split do you see there? Over here, I have to split it, right? You see that? So that line equation versus a circle equation. And over here, 2 circle equations. You see that? And in the remaining part, you have line bottom there and up there, circle equation. So you have to divvy up this one into 3 different regions. Then what? And integrate, with the old square root in it. A little bit nervous. But if you look at it as a polar coordinate, and it's a lot clearer. Look at the boundary. I think how to analyze this region is looking at the boundary, understand it from there. This is a boundary here, right? What's common in that boundary? Radius is always a, fixed. What about this boundary? Radius is fixed, but you can see the theta is changing, right? If you see that here, theta is fixed. Angle is not changing, but the radius is increasing here, right? If you look at it here, theta is fixed, but radius is increasing. So by looking at this boundary, you can see that, r is varying from a to b. Theta is varying from alpha to beta. And then one last thing you have to check is that, is it really independent? If I given r, usually they say the given theta first. Given theta, is r can really independently vary from a to b, or given theta, r actually varies from something to something depending on theta. So if theta is fixed, for example, somewhere here, some arbitrary theta in between alpha and beta, r varies from, go through all this fixing that theta, go through all these points and checking that there is no hole in there. This entire segment is contained inside the region, right? You don't have to break this. So r actually varies from a to b. Doesn't depend on where theta is. That's one thing you have to check. You have to given theta, r really does freely vary from a to b. Right? So this is xy space, correct? But what is the parameter space? What are the 2 parameters we're using here? R and theta, right? R and theta, the 2 parameters, s and t. Right? This is non-linear, everything is bent around. Because they usually set it like this, given theta, how is r varying? They usually put theta down here. Given theta, how is r varying up here? Alright? How is theta varying here in this picture? Alpha to beta, so you put alpha to beta here. Usually this alpha to beta is a number in between 0 and 2 pi, right? How about r? How is r varying? Yeah, a to b. So these are usually positive number, right? It could be arbitrarily large too. They're freely varying like this, and you're creating what kind of region? Nice rectangular region. Correct? Yeah, this is a free region like that. So if you have an integral over this region D, and you have to integrate something like this, this is not iterated integral, it's a double integral. You can actually integrate over that, right? Over that, so that's going to go R. We'll put R down there. And this x and y is parameterized in terms of r and theta, right? So you write that formula and replace x and y with r and theta. And then you have to multiply. This is they usually write dr d theta. Or not d theta, dr. And then you have to multiply the Jacobian factor. Let me put like this. What is that parameter down there? R theta in that order. Okay? So here's a picture. If I select a little bit here, theta is varying tiny delta theta, and r is varying tiny there. How is this one just going to correspond with a bit of exaggeration? It is like this. So it's not parallelogram. This one is stretched around like this. And they're saying this, the area of this one and that, what is the ratio of this area? Roughly is this guy right there. That's the ratio. This number at that point indicates that it's a 5, that the area of that one is a 5 times of that area. That's what this factor means. But if you go to slightly different place, that stretch factor is different. Yes? It's not linear. It's not linear. That's why it's all not a parallelogram and it's approximation. And they're claiming this approximation is good enough to compute this integral. Alright? Fair enough? So, who remembers the polar coordinates? You're just reading this one? Well, yes. Alright, so what is our first exercise today? Yes, we can compute the Jacobian matrix right there. Yeah. Alright? So there is our xy. Do you remember how we line up column vector, right? Rewrite it as a column vector. First column vector, and order of this r theta is also important. R is our first parameter and theta is our second parameter. Right? You can also write down the formal version. Let's write down the formal version like that, right? You write x and y down there like that. X and y. Fair enough? What is our first parameter? R. So you put R there. Second parameter? Theta there. That's all you have to compute. What is this called? Jacobian matrix of this parameterization. Right, was it good? Yeah, you write down xy, look at x and differentiate with respect to r, cosine theta with respect to r, sine theta. And then the other way around. Good? So what is the determinant of this guy? Yeah, you multiply these two, right? So what is it? R times the cosine square theta? Minus, multiply these two, that is negative r sine square theta, right? Then r is common factor. And you end up at cosine squared plus sine squared. Famous Pythagorean identity gives you r. So if it is a polar coordinate, you're not going to be computing Jacobian all the time. Just memorize the Jacobian. What is the Jacobian for polar coordinates? R. Okay? That's the answer. So, and it's a positive number, right? R positive number. What does that mean? It's a good orientation. It preserves the counterclockwise rotation of first vector and the second vector. And they stated like this. And they gave independent explanation of why this is true in the book. I encourage you to read that one. But in general, the principle is this thing that it is applicable to a lot more things. So yeah, it can be 0, but that means if it is r is 0 and in a region where the area is 0, just like 1 point, in the integral it doesn't matter. Like integral in one variable integral, what happens over there if there's discontinuity like that? Integral is not really affected by what happened at the just tip point, but something bad is happening over some reason that affects the integral. Just like that, r can be 0, and just putting the 0, if it is really small region where the area is 0, like tip point, then it's it's not causing any problem. R being 0 means everything is inside 0, 0. Because no matter what your angle is, if you multiply r 0, everything collapses down to 0, 0. Right? So if you're looking at this type of thing, and if your region D is polar friendly, if it's just like this one in here, that one there, right? Region is like this, and then your polar region is very rectangular, and is much easier for iterated integral purpose. So you will switch that to here. As you can see, x and y is parameterized by this r and theta. And what are you multiplying here? R. Where did that come from? That's our Jacobian factor. All right? Okay. Example. First goal is analyzing the region D and understand this is good for polar region, polar transformation. So let's write this one down, the problem, and then I'll address the first question. Evaluate the double integral in the region D of log x squared plus y squared, and D is described like that. Right, first part of the second exercise, go and sketch this region and come up with this inequality for r and theta. And it's actually a rectangular region. Right, so sketch the region. And find inequalities for r and theta. That's it. And so it's better to state it like the given theta being something and something, r is from something and something. That's how iterated integral built around, right? So in that order, so quantifier better be there. Yeah.
When theta vary from 0 to pi over 2, so it's only the first quadrant?
Oh, my first quadrant. Yeah, I missed that. Thank you. I don't know. It's a slice of pineapple. That's come to my mind. So when you see the slice of pineapple in front of you, yeah, it's not so delicious looking, and then you can think about, okay, I'll think about something else. And all right. All right. That's your answer? Given theta, it doesn't go beyond 0 or pi over 2, and to draw the random line of this theta and understand theta r always vary from 1 to 2. Here in theta r very slightly different, over there theta slightly different, then you have to involve theta in here, but in this case it's not because of circle. Yes, sir. This is the square root is a 1 to 2, not 1 to 4. Okay? Fair enough? Yes.
Really elementary question. Where is 0 and where is pi over 2?
0 is here. This is called standard position. 0 is always positive x-axis, and counterclockwise is where theta increases. So here is pi over 2. Okay? Go over pi here. Right? This is called standard position. Cylindrical, spherical all rely on the same orientation. Make sense? All right. Question about this one? Okay. So what is question number 2 then? Still in exercise 2. We're going to calculate this guy, right? Compute the integral. But before we do that, let's recognize, is this a rectangular region or not in xy plane? It's not, right? It's not a rectangular region. It's just like pineapple region. However, if you look at theta r plate, what is it? Parameter space between 0 and pi over 2, r varies from 1 to 2. So that's this rectangular region in this parameter space, right? And that's why we're doing this one. This is good. Over this one, iterated integral would be a lot cleaner. Right? So what was it? Yeah. It would be fancy Fubini's theorem, right? You're doing not like this slice, that slice is going to be very different slicing. It's like a curved space slicing, right? So it's a lot fancier version of a Fubini's theorem, yes. So change of variable is ultimate generalization of Fubini's theorem, yes. It's a good analogy. Try to remember that formula from going from d to r, right? Integration over d to integration over r, then enter iterated integral. Don't try to write down iterated integral first. Yeah. So let's remember the Jacobian factor. What was the Jacobian factor? R. Yeah, R. That's what you have to throw in. Before we enter actual iterated integration, let's focus on switching from integration over xy plane for integration over r theta plane, right? Right. This is how you have to replace x and y with your parameterization. And because of this x squared plus y squared still pulling out cosine squared plus sine theta squared plus sine theta, it simplifies a little bit. That's usually when we do this. There's something that a lot simpler than xy coordinate. So you enter this integral. Then you can look at this as just another double integral with r and theta in there, right?
And you can pull out the square root of the r.
That's true. That's usually what I would do. But I realize that if I just do the u substitution eventually here, then it kind of cancels the r out there. I think it saves a little bit of integration. And I thought maybe that's not what I'm going to do, but normally that's what I would do. Yes, yeah. Right. So make sense, this switch? Any question to this switch? Then see if you can write down the iterated integral from here. From there, go to iterated integral. That involves r and theta. R varies from where to where. Theta varies from where to where, right? Right. And it's good over here. Look at this r theta parameter space. Parameter space right there. How is r theta varies? Independent from each other. Right, I just formulated, didn't integrate anything. You can check the answer in there. I do theta first because there's no theta in there, right? If you integrate it, everything is constant. So I thought that's nicer. Then you do integrate r. So this is my order of integration. So how's your integral going? If you do a theta integral inside first, nothing happens to this multiplicative part, that all in R, right? So this stays there, and we pick up pi over 2 factor, so it goes outside. It's all about computing this integral, which is just one variable integration problem. And I think you could have done the integration by part directly there. I don't know. You could try that. You might have ended up at 2 integral, but I did the substitution first because I see r squared and r there. So switch to just ln u integral. For that one, you have to use integration by part, using this invisible 1 in there. Integrate 1, and then you pull out u in there, right? Then differentiate ln u, so it's u1 over u, become 1.